Hello everyone! In today's video, I am going to cover some basic organic chemistry concepts, including how to draw structures, how to draw curly arrows and what they represent, and also what are electron sources and sinks. So the first thing we need to cover is the bonding of carbon. So carbon in organic chemistry usually forms four bonds, other than very rare cases that we are not going to touch in a long while, and definitely not in this video. So for right now, for practical purposes, let's just remember that each carbon forms four bonds. So these bonds can be formed with other atoms such as other carbons, other hydrogen, nitrogen, oxygen, chlorine, or other halogen atoms. It's there's a lot of possibilities here, and I think the best way to learn about how each type of bond behave is just to look at more reactions and have a general sense of their similarities and differences. So there are three typical shapes that a molecule formed with carbon can take because carbon forms four bonds. So the first one is the tetrahedral structure. So that's a structure where the center carbon is bonded to four other atoms with sigma bonds. So by now you should have already learned that electrons are not localized as suggested by dot and cross diagrams. So in a dot and cross diagram, you might draw something like this. So you might have a carbon in the middle. You have your four electrons from carbon, then you have your four electrons from the four hydrogen atoms, and you have your four hydrogen atoms. So unlike what the dot and cross diagram suggests, the two electrons are actually, firstly, they're not different from each other, and secondly, they aren't so-called localized inside the bond. So the bond is something that we have constructed or we have imagined to explain organic reactions, but the bond is not something that we can it's not something tangible that we can just touch and see. So it's more it's more like a region where the electron is likely to be found. So that's the thing about electron orbitals. It's not that you are going to see this shape, although there are research that suggests you can see this nowadays. It's rather just a probability, a space with a region of space with a high probability that an electron is going to be found in. So it's all about probabilities. So that's something to keep in mind. You can't say that electron is at one exact place. You can't say it in a very in a same manner you say that I know the bottle is on my desk. You can't say it that way, but you know that the electron has a high probability of being in an orbital, being in an atomic or molecular orbital. So we are not going to bother ourselves with that. Instead, we are just going to draw the bonds and deal with them. So let's move on to this first case. So the first case is you have a carbon, it's bonded to four other atoms, and because of VSEPR theory that suggests that the electron groups want to be as far away from each other as possible to minimize repulsion, um, you will have the four bonds each placed 109 degrees away from each other if the four bonds are if the carbon is bonded to four groups of the same nature. So if all four atoms are hydrogen, then yes, the bonds are going to be 109 degrees away from each other. And if the carbon is bonded to four different or different atoms or different groups of atoms, then this angle might vary slightly, but not a lot. So one way to visualize this tetrahedral structure is that you can draw yourself a cube. Okay, you can draw yourself a cube, Then if your carbon atom is located at the center of this cube, then your four groups attached to carbon will be located at the four vertices of this cube. So if you do your trigonometry, you will find that the angle is approximately 109 degrees. Now let's take a look at this case. So in this case, we have a carbon attached to three other atoms or three other groups of atoms. So here, there's both a sigma and a pi bond. So the sigma bond is probably going to look something like this. While the pi bond is going to look something like this. So here, the sigma bond is through this axis, so the sigma bond can rotate freely, but the pi bond restricts this rotation because this lobe of the pi orbital overlaps with this lobe, and this lobe overlaps with this lobe. So the sigma bond is what we call a head-on overlap, while the pi bond is what we call a side-on overlap. So that's a distinction that we should keep in mind. For now, we should just take note that the angle here is approximately 120 degrees because the three electron groups want to be as far away from each other as possible. So even though we have four electrons here in these two bonds, in the sigma and pi bond, they're counted as one electron group because they are formed between the same two atoms. So these two cases will be more common in the reactions we are going to deal with at this basic level. So you should probably keep these two in mind. Then the last case I'm going to cover here is the linear case. So an example of this linear case is carbon dioxide or CO2. But usually we don't consider carbon dioxide an organic molecule. It's just here to show the bonding. So the bonding is 180 degrees because these two electron groups want to be as far away from each other as possible. So both are one sigma bond and one pi bond. Now I'm going to explain a concept called valency. So valency is just the common or normal number of bonds a atom forms. And for carbon, it's four bonds. But when you plug away one of the atoms at the end of one of the bonds, then the bond pair might go to either carbon or that atom that's been plucked away, right? So if the bond pair goes to carbon, then the leftover three bonded carbon will now have one more electron than neutral. So it will take on a negative charge, and that's what we call a carbon anion. And if the bond pair goes to the atom that is being plucked away, then our carbon would be taking on a positive charge, and that's what we call a carbocation. So these are the cases, these are the forms of carbon that we are going to see that's quite common in organic chemistry. So the next atom that appears quite frequently in organic chem is oxygen. So you can have a two-bond oxygen, and that's the most common example of that is just your water, so H2O. The oxygen is bonded to two hydrogens, and similarly in organic chemistry, you can have your oxygen being double bonded to a carbon, or your oxygen with one bond to carbon and one bond to hydrogen. So all of these are very common. And the other one is the hydroxide anion. So that's your O with a bond to H and a minus charge. So in organic chem, you can the O might be bonded to a CH3 group and still bear a negative charge. So that's your one bond oxygen with a negative charge. So that's your typical valency of oxygen. And then you will have your nitrogen, which can form three bonds or four bonds with a positive charge. So your typical examples are your NH3 and NH4 plus. And for hydrogen, it can bond to a halogen atom. Uh, and that's your typical example of your one bond hydrogen. So the X here represent a halogen atom, or the H can be bonded to a carbon atom. So hydrogen usually forms one bond unless you have your H plus, which is your hydrogen cation. So that's pretty common when you have an acidic media that you're carrying out your reactions in. And H plus is basically what makes your acid acidic. And you might also encounter something called H minus, and that's your hydrogen anion, but that's much more rare than H plus because H minus is not very stable. And then you have your halogens. So it's your chlorine, bromine, and other one bonded other atoms that likes to form one bond. So in this case, you can have your HX, so that's one bond to hydrogen, or you can have your CX bonds, so that's one bond to carbon, and X here just represents the hydrogen, sorry, the halogen atom, and you can have your X minus, so that's your X minus, that's your halide ion, and your halide ion can and your halide ion can, the leaving of a halide ion can result in the formation of a carbocation. So that's a reaction that we are going to cover only later on. I realize that this one should probably be a 17 because these are group 17 elements. Okay, let's move on to the next slide. So, one thing that we do in organic chemistry is that we make a lot of simplifications. So, in terms of drawing structures, you might have seen that we draw this kind of structure shown on the screen called skeleton structures. And here we draw all the bonds as lines. So, if we have double bonds, then we have double lines. And the CH bonds are implied because we know that each carbon forms four bonds. So the bonds that are not seen or are not shown on a diagram are implied to be CH bonds. And we need to write out all elements other than carbon and also write out hydrogens that are not attached to carbon. So for example, hydrogens that are attached to nitrogens. And we can also use some abbreviations such as Ne for the CH3 group and an ET for the CH2 CH3 group. And we're going to cover other abbreviations next time when we encounter them. So for now, let me explain what this skeletal diagram means. So here, we know that all the vertices here are carbon. So we can just draw out the carbon here. So all these are carbon atoms, and then because here we have one and two bonds, we know that this carbon must be bonded to two hydrogens because it must form four bonds. Then here we must draw out the hydrogen because it's attached to nitrogen and not carbon. So here we see that there are already three bonds to this carbon that's being drawn out. So we can draw a fourth bond that's connected to H because only CH bonds are implied. So you might ask that we have encountered carbon cation and carbon anion on the previous slide, and how we're going to represent that. Well, if we have this is really unstable, but let's say we have a carbon cation here, meaning that for some reason the chlorine just flew away. If this chlorine flew away, then if we don't have this, then to make it clear that we have only a C attached to a H, the C is only attached to H and to N and to another C and not to another H. So we want to make clear that this fourth H doesn't exist. Then we need to put a plus charge that is circled here near C. So that makes it clear that this is a carbocation and not just a H that is not drawn out. Yeah, so in this case, the chlorine is here. So let's talk about other things. So here we see that the carbon it has one, two, and three bonds. So obviously the fourth bond would be a CH bond. And so all the hydrogens here, one, two, three, four, and five are implied. So these carbons are attached to two other carbons as well as one hydrogen. Now, for this carbon, you have one, two, three, and four bonds drawn around it already, so it's not attached to another hydrogen. So let me just demonstrate how we use the abbreviation. So let's say ET. So if I draw something like this, that just means that is the equivalent of drawing this. So this is your CH2 group, and this is your CH3 group. So drawing skeletal diagrams, understanding them really takes a lot of effort and really takes a lot of time as well. So you should really practice. So another thing we can do is that instead of drawing out this OH bond, if it's not very important, if it doesn't participate in any of the reactions that we're interested in, we can simply write OH here. Similarly, instead of drawing out this NH bond, we can just write the H directly above N. But if you want to show how this bond participates in reactions, then yes, you need to draw this bond out. So just because we can imply CH bonds and also not write out elements such as carbon and hydrogens attached to carbon doesn't mean we can't show them when we want to make it clear or we want to emphasize that part of the structure. So these three rules just correspond to the bare minimum that you need to draw, but you can draw the structure in more details and it will still be correct. Okay, so in this slide, I have gone through how we draw structures that are in 2D. So how do we draw 3D structures? How do we represent how molecules look like in three-dimensional space? So here we are going to use something called the dash and the wedge. So here, this is called the wedge. So the wedge is very strong, so it comes out of the page, while the dash is quite weak, so it goes into the page. So what do I mean by that? Well, single bonds can rotate, so it's so drawing this is the same as drawing this. However, you know that these two bonds can't just exchange positions, meaning H cannot be here while Cl is here without breaking any of the bonds. So the two bonds don't just swap. So all of the single bonds, so you have one, two, three, and four that are bonded to the central carbon, all of them can rotate by themselves, but they can't really swap with each other. And the wedge represents the out of page direction, while the dash represents the into the page direction. So the 3D orientation or the 3D structure of this molecule is really fixed. So when you draw this, it can only mean one thing. So that's really specific. So what does this structure mean? Well, this structure corresponds to this diagram here. And as you can see, this CH2, CH3 group, so this CH2, CH3 group represents the CH2, CH3 group here. So as I said, because this single bond can rotate, this is the same as this, and that's why this part of the molecule is represented. Then for this CH3 group, we didn't draw the hydrogen, but of course they exist, and it represents this part in three-dimensional space. Now for the chlorine here, for the green atom here, it's pointing out of the page. So here it's pointing out of the page as well. Then this H is going into the page. So it's going into the page inside the diagram. So if I draw out a plane here, so if I align, let's say I align these two bonds on the page. So I draw out a plane here that these two bonds cut through. So this plane is on these two bonds. Then this bond will be poking out of the plane while this bond will be going into the plane. And that's what the dash and wedge means. Similarly, drawing 3D structures, the 2D structure rule still follows. So you can not draw out the hydrogen. So both of these are correct. And both of these correspond to this. So it might take a while to get used to. So if you draw out something like this, then these two are actually, sorry, let me go back to the previous page. Then these two structures actually look different in 3D space. But if you draw something else, like if you draw something like this is the hydrogen, then this is the ET group, while so this one is going out, coming out. So this is a wedge. Then you have a dashed chlorine. Then these two structures are actually the same in 3D space because you can just rotate around this bond and you will get this structure. So it takes a long while to see how you can how some structures look the same or different in 3D space, but in today's lesson, we're just going to learn how to represent them. So this is good enough. Now, an important thing I want to cover and focus on is partial charges. So this has something to do with bond polarity. So the more electronegative atoms like electron more, so they will pull bond pairs closer to themselves than less electronegative atoms when these two are bonded together. So for example, when you have carbon bonded to a chlorine, then because chlorine is more electronegative, then the electron pair wants to be located closer to chlorine than to carbon. So of course, the electrons are not localized, but they want to they have a greater tendency to be nearer to chlorine than to carbon. So the bond polarity here is that the chlorine is partially negative while the carbon is partially positive because the bond pair tends to be pulled towards the chlorine atom, and that is why. Okay, so this is something that we use to show bond polarity, and the bond polarity for this side for chlorine is negative, partially negative, while for carbon is partially positive because chlorine is more electronegative. So in the case of CH bonds, CH bonds are not very polarized because carbon and hydrogen have similar electronegativity. So you're going to see bond polarity more often when you have bonds such as OH bonds, CO bonds, or you have your CCl bonds or any bond of carbon with halogen. So these are very polarized bonds, and the halogen would usually have a partial negative charge while the carbon will have a partial positive charge. So, for example, in a CO single bond, the bond pair is closer to O than to carbon. Of course, here we are thinking in a very localized model, but if it helps you, then by all means, think of the bond pair as being closer to O than to C. And that is why the more electronegative atom here, that is oxygen, will have partial negative charge, while the less electronegative atom here has a partial positive charge when the O and the C are bonded together due to the so-called position of the bond pair. So the representation of the partial positive and negative charge are the delta plus and delta minus here. And you can just label the atoms with these two representations, and that will inform you and also the reader which atom, where the like how the bond polarity is, and how the bond, the direction the bond might break towards. And that's something we are going to be quite concerned with in the next video. So another thing that people often confuse with partial charge is formal charges. So imagine yourself break all bonds around an atom homolytically. So imagine you have something like Cl, H, H, H. So if you have something like this, a four bond carbon, you are going to cut all these bonds in half. So the carbon has exactly 4 electrons around it, while the other atoms, well, the hydrogen have 1 electron around it, and the chlorine has 7 electrons around it. So the formal charge is just the number of electrons the atom has after this imaginary bond breaking process minus the number of electrons in a free atom. So the number of electrons in a free carbon atom is 4 because carbon is located in group 14 of the periodic table. So it usually has four valence electrons, and after you break all the bonds homolytically, it still has 4. So the formal charge of carbon is 0. And the same goes for chlorine. Used to have 7, now still have 7. So that's so its partial charge. So its formal charge is 0. The same goes for the 3 hydrogen atoms here. But if we have something like NH4 plus, so you have your NH, H, H, and H. Then you have an overall plus charge. Then when you break all these 4 bonds imaginarily, then this hydrogen will have 1 electron. Like all 4 hydrogens will have 1 electron, while this nitrogen will have 4 electrons. However, nitrogen is located in group 13 of the periodic table, and normally it only has 3 valence electrons, but now it has 4. Nitrogen is located in group 15, and usually it has 5, and now it has 4, and that's why it has a formal positive charge. So one way we can represent the formal positive charge is, instead of drawing this bracket with a charge thing, we can just label a plus near the nitrogen and we circle it. And that's how we represent a formal positive charge. So yeah, the representation is just a plus or minus. You can circle it next to the atom. And these formal charges usually are due to the formation of dative bonds. So in this case, the nitrogen donates its lone pair to the hydrogen, to a H plus ion. So the reaction that lead to this is NH3 plus your H plus, and the lone pair on the nitrogen actually goes to pick up this H plus ion, and then you have this structure. So that's what we call dative bonds. So in your Lewis acid and base theorem, it's just the donation of a lone pair from the Lewis base to the Lewis acid. So this usually results in the formation of formal charges. So instead of representing it with a bracket and a plus and a dative bond, we can simply write a plus near the nitrogen. And yeah, so the nitrogen has a formal charge of +1. So that can be calculated with this equation as well. But after a while, you just get used to it and you can just label it on the go. So here you have your nitrogen donating its lone pair to an oxygen. So something that you can write here is that you can write a minus next to the O and a plus next to the N. So overall, this molecule is still neutral, but its atoms can have formal charges. It's just overall, these formal charges cancel out to give you a neutral molecule. So in this case, you can imagine yourself having breaking all these bonds homolytically. So the nitrogen will have 1, 2, 3, and 4 electrons around it after you break all the bonds. And these 4 electrons are one less than the 5 electrons that the nitrogen usually has in its valence shell, and that is why the nitrogen will have a formal positive charge. Then for oxygen here, if you break this bond homolytically, then you have 7 electrons around it, and oxygen usually has 6. So this is a formal negative charge here. So take note for atoms that or elements that are in the first two periods of the periodic table, you should prioritize the octet rule. So the octet rule should not be broken other than in very rare circumstances for the first two periods. So you might have less electrons than 8, but you shouldn't have more. Now, we are also going to deal with something called resonance structures here. So, for example, when we have an ion like this, or it can be a neutral molecule, it doesn't matter, then you can push your lone pair here for it to become a bond, and then this bond can come here. Or alternatively, this bond can come here. So the valency of each of the atom do not change, but where the lone pair is positioned can change in resonance structures. So these three are called resonance structures. No, they are not the same structure because if we label each of these oxygens so that they are different from each other, you can see that the charges, the negative charges and the bonds, the pi bonds are positioned in different places. So they are different structures when you are considering resonance structures. And when you are drawing resonance structures, you shouldn't break or form any single bond. So you shouldn't break these bonds so you can have your O2 minus and S plus. This is illegal. And at least in traditional terms, and you should usually avoid charge separation. So for example, you shouldn't do this. So you remove this bond. So you shouldn't remove this bond and then label this minus and this plus. So you have two minus here, but a plus here, then that results in a really unstable resonance structure. So it is still a different resonance structure. It's just that it is unstable and doesn't contribute as much to the overall structure. So the real structure or the resonance hybrid is a weighted average of all resonance structures depending on how stable they are. So in this case, all three are equally stable. So each of them contributes 1/3 to the overall structure. So overall, the minus charge will actually be delocalized across all three oxygen atoms. And the bond order between the sulfur and oxygen here will probably be more than 1 but less than 2 for each of the SO bonds. However, we know that um, we know that the resin structure that looks like something like this isn't going to be very stable. So when we are considering what's the average structure or resonance hybrid, we are probably not going to take this structure into account. We're not going to take it seriously. So the real resonance hybrid will probably just be a hybrid of these three. So these three are the significant contributors, and when we're drawing resonance structures, we are probably only going to draw these three. Okay, so having covered this, I'm going to cover something called electron source and sink and also the curly arrows. So electron sources are nucleophiles, but electron sources usually refer to like specific atoms or specific regions of molecules, while nucleophiles refer to the whole molecule. So phile just means um, loving, and here nucleo just means something like positive, because the nucleus is positively charged, so it likes to interact with positive species, and that's why it's nucleophile. So nucleophiles are electron rich because it likes to interact with electron poor species. And electron sources can also be anions or atoms with formal negative charge, atoms with partial positive charge. Notice that these two are very different things, and in a while you will see why. And you can have lone pairs or pi bonds acting as electron sources as well. So a nucleophile usually has a nucleophile usually refers to any of these things. So it can be any of these. Now, for electron sinks, or where the electron likes to go to, we call the whole molecule electrophiles. So electro for electrons, philes for loving. So it loves electrons, so it wants the electrons to come to it, and that's why it's called electrophiles. And you can have your cations, atoms with formal positive charge, partial negative charge, or atoms with an empty orbital that the electrons can go to. So these are electron sinks, and the electrophiles can be any of these. And I will demonstrate what are electron sources and sinks later on with examples. So you can recall the Lewis acid and base theory, or go and rewatch the video I made a while back. And similar to how Lewis acids react with Lewis bases, nucleophiles react with electrophiles. And after the reaction, the electron source becomes the electron sink and vice versa. So the nucleophile becomes the electrophile and vice versa as well. So in this case, you can think of nucleophiles as your Lewis acid, while your electrophiles are your sorry, you can think of your nucleophiles as your Lewis bases, while you can think of your electrophiles as your Lewis acids, because nucleophiles are electron rich, while electrophiles are electron poor. So electrons always go from the rich to the poor species. So the electron always goes from the electron source to the electron sink. So curly arrows indicate the movement of pairs of electrons. So they always point from electron source to electron sink. So bonds both form and break towards electron sinks. And the valency typically doesn't change. And you can refer to slide 3 for some typical valencies of atoms we deal with in organic chemistry. So I'm going to demonstrate electron sources and sinks with examples here. So in this case, the Br minus has a partial negative charge, while the carbon here has a partial positive charge. So in this case, the Br here is the electron sink, while the carbon here is the electron source. So in this case, the bond pair here will likely go towards the bromine rather than the other way around, and that's why this bond can break. So your carbon is your electron source, while your bromine is your electron sink. Then after the reaction, we notice that we have a carbon ion here that's going to act as a electron sink, while you have a bromide ion here that has a lone pair and can act as an electron source. So if the reverse reaction were to happen, then the cation, the positively charged carbon will be the electron sink, while the bromide ion, the lone pair will be the electron source. So the lone pair can go in and attack this positive charge, and again, the electron flows from the source to the sink. And you can notice that this arrow is exactly the opposite as this arrow, and that's the beauty of organic mechanisms. And that's basically how electrons flow. So if in the forward reaction it flows this way, then in the reverse reaction, if that were to happen, the electron will flow the other way around. Now, for the second example here, we have something similar. So the carbon cation here is the sink, while the lone pair here on the hydroxide ion is the electron source. So the source attacks the sink, and basically the two sides swap position, and the sink becomes the source and the source becomes the sink after the reaction. So that's an example of bond forming between ions or opposite charges. So you can notice that these two reactions are just opposites of each other, and that's that's true for a lot of organic reactions. So you have your Diels-Alder reaction and you have your retro Diels-Alder reaction. So from the retro, you know that the two reactions are opposite of each other. So for a lot of organic reactions, you're just seeing opposites of each other. And whether one will occur over the other is just a matter of favorability and yield. And that's not going to be something that we're going to cover here, but it's something that you should know that a lot of reactions are reversible, and yeah, and you need to consider whether the forward one is more favorable or the reverse one is more favorable. Here we're just going to talk about curly arrows. So let's move on to the next slide. And here you notice that the curly arrow looks a bit different. So here, instead of having this full arrow, we have half arrow. So the half arrow just means that it's one electron instead of a pair. So here we have two electrons in a bond. Again, we're using a localized model, but the two electrons aren't really like side by side in a bond, but we're just going to consider them as these two dots that can move, okay? And so the first curly arrow means that this dot on the left will move to one of the bromine, while the second dot moves to the right. So the bond breaks exactly in the middle. Although that's not really what happens, but if that helps you picture it, then by all means, go ahead and picture it that way. And the opposite of this reaction is actually this. So we call these species, we call them radicals. So radicals are species with an unpaired electron. So if we have OH, but instead of minus, we have an unpaired electron here, and the overall species is neutral, then this is also a radical. So when a single bond or a bond forms between radicals, you can get back a molecule, and yeah, these two are just reverse reactions of each other. Thing I'm going to go through is called functional groups. So please note that there are more functional groups than shown here, and a molecule can have multiple functional groups. And as you can see here, many functional groups actually share the same part of the molecule or the same atoms. And for in this case, it's the CO double bond, and we call it the carbonyl group. And because of that, all these functional groups actually react pretty similarly, as in they undertake the same kind of reactions. However, their reactivities differ. And so because of this, we say that each functional group had their own characteristic reactions in terms of reactivity and also the type of reactions. And we shouldn't we shouldn't say that one functional group cannot undergo this reaction just because another one has can undergo that reaction. And also when we have multiple functional groups in the same molecule, then different parts of that molecule can react and they can have a preference for what type of reaction they undergo. So if we want this part of the molecule to react instead of the other parts, then we need to consider the reactivity of the other parts as well. Another thing we need to take note is how we classify atoms. So if it's attached to one, two, or one, two, three, or four other carbon atoms, then we call it primary, secondary, tertiary, or quaternary respectively. So what do I mean by that? Well, tertiary amine means that the N is attached to three other C atoms. And if we talk in terms of carbocation ions, so for example, this is considered a tertiary carbocation ion, while this is considered a secondary one, and this is considered a primary one. Here should be 2H. So that's considered a primary carbocation ion. So you are going to look at the atom that provides the functional group, and then you're going to determine how many carbon chains are around it. So in this case, if you have a ET group rather than Me group, this whole ion is also known as a tertiary carbocation ion. So there will be some significance to whether an amine or carbocation ion is primary, tertiary, or secondary. We're not going to deal with them now, but it's good to know that when another person is saying secondary carbocation ion, they are referring to this. So we often use something called the IUPAC for naming organic molecules because we want people to know what molecule we are talking about in a very efficient manner. And if we want to study how we name our molecules, then it's pretty useful to take a look at this guide. And the guide has everything summarized. It has everything you need to know about how we name molecules and it's just good to know. In terms of reactions, we can draw out the molecules, and that will pretty much give us information about what reactions they undergo. So, in terms of Olympiads, knowing the names of molecules is not that important, but in terms of research or in terms of real life, yes, you definitely need to know them. In Olympiads, they usually just draw out the molecule for you already, so you don't need to be concerned about how to name them. However, there are times when they say that molecule A reacts with molecule B, where they gave you the name of molecule A and B, and then you need to figure out what they are and what the final product is. So in those cases, learning about the IUPAC system is very necessary. So I think yeah, it's important to take a look at this guide. But I'm not going to spend time in this video going through everything because there are a lot of details in there that you should take a look for yourself. And something else that I'd rather spend my time on is the trivial name of very important molecules around us. So acetic acid looks like this, acetyl chloride looks like this. So note that for you can notice that when you have the acid prefix, that's usually something. that looks like this. And yeah, that's pretty much it. And for all the benzene derivatives here, they are often used as solvents, so you should probably take note of them. We have trivial names instead of using the IUPAC names for these molecules because they're so important and so common in organic chemistry and organic synthesis that we have retained their names that are being used a long time ago, and we are paying tributes to those names. And sometimes those names are easier to remember, and that's why we are using these trivial names. And yes, these trivial names can be used in organic synthesis schemes, and you are going to see them. So it's a good idea to familiarize yourself with them, if not memorize them. And actually, I've reached the end of all the content I need to cover. And here are some questions that you can take a look at and try to test yourself with. These questions are not very difficult, and most of the answers can be found online. However, if you need any help, feel free to reach out in the comments, and I will try my best to answer your questions. And these are some references and resources you can take a look at if you're very interested in this session's content. And a lot of these resources cover what I've gone through in greater detail. And I think it would be really helpful for you to understand them as well if you have the time and energy for it. And that's it for today's session. I hope you enjoyed it and see you next session.